of the event occurring between said range, we have to use the table for the integral, right?
Yeah. That's what I believe.
Yes, sir.
Yeah.
Okay. Thank you, sir. Thank you very much, sir.
Yeah.
Can start.
Okay. So we can start
Recording in progress.
today's class. So I will next talk about temperature measurement. In fact, we are going to talk about measurement of various physical quantities, starting with temperature and then pressure, flow rate, and other thermophysical properties. So temperature measurement is very important, for various applications, starting from daily life to industrial application, as you would have realized. So here the objective is to look at the fundamentals of temperature measurement and then look at some of the sources of errors that can come up during temperature measurement towards the end of this chapter. So let us first ask ourselves what is temperature. Basically, we should try to understand the definition of temperature. So as you all know, temperature is an intuitive concept. In layman term, temperature would mean that it is the degree of hotness or coldness. Typically, if something is hot, you say that it is at a higher temperature. And the contrary, if something is cold, you say that it is at a lower temperature. So that is in layman term, but if you were to give a technical definition of temperatures, then we have various definitions that I would present one by one. So first, you could actually, define temperature from kinetic theory of gases. As you can see here, you can say that temperature is related to average kinetic energy of ideal gas molecules. As you know that in a gas, the molecules are in a random state of motion, and the molecular velocity is indeed a function of temperature. So from kinetic theory of gases, you can say that the kinetic energy of a molecule, which is given by half m into v square, v is basically the root RMS, root mean square velocity of molecules. So half mv square, the kinetic energy will be equal to the thermal energy, and the thermal energy is given here as 3 by 2 into kb times temperature. Kb is basically the Boltzmann constant, which has a fixed value of 6.023 × 10⁻⁻23. And you have the temperature, which is in absolute temperature scale. So you can define temperature as the ratio of the kinetic energy scale to the Boltzmann constant. Okay, this is how you can define temperature from kinetic theory of gases.
Sir, can you please spell the name of the constant, sir? I'm sorry.
Sorry?
Can you please spell out the name of the constant?
This is called Boltzmann constant, Boltzmann, okay, Boltzmann constant. And
so value?
The value is 6.023 into 10 to the power minus 23. Okay. So you can actually, define temperature in this way as the ratio of the kinetic energy divided by the Boltzmann constant. Okay. Then you can define temperature from second law of thermodynamics. So, as you know, that from second law of thermodynamics, heat would flow from a higher temperature to a lower temperature in the absence of external effects. Okay, External effects meaning if you supply some energy, external energy, you can also pump heat from low energy, low temperature to high temperature, like that we see in a refrigerator. But in the absence of external effects or external energy coming into the system, you would see that always heat would flow from a higher temperature to a lower temperature. Okay, so you can define temperature this way from second law of thermodynamics. Then you can also define temperature as the derivative of reversible heat with respect to entropy. Okay, so if you go to thermodynamics, you have a system and you do reversible heat addition, then that can be expressed in terms of temperature times the change in the entropy of the system. Essentially, you can say that temperature is basically the heat, reversible heat added to the change in the entropy of the system. Okay, so this is again another definition of temperature.
Okay, sir, just one question I want to ask.
Yeah.
This, like the kinetic theory of gases, there are some assumptions that like the collision between molecules are elastic, collision between the gas molecule and the reservoir is elastic. There are many assumptions in that.
Mhm.
So taking that assumption, this equation is made, if I'm not wrong, right, sir?
So this equation is made that what is the source of the kinetic energy of the molecules? The kinetic energy of the molecules is because of the thermal energy inherent in the gases. Okay, so the thermal energy is basically expressed in terms of Boltzmann constant times temperature. So by equating the two, you can actually get a definition of an expression for
So-
temperature, and so you can.
So this is a real number, right? So in that sense, right? There's
Yeah,
no
yeah.
assumption in that.
Yeah, there is. I mean, this is basically you say that it is ideal gas. Okay, that
okay.
means the molecules are non-reacting. They are, they do not change their constituent frequently. And so under those assumptions, you can actually write this kinetic energy and thermal energy are equal.
Fine, sir. Thank you.
Yeah. So then you can talk about zeroth law of thermodynamics. Zeroth law of thermodynamics says that if there are two systems which are interacting through a wall, and if the two systems are in thermal equilibrium, that means heat, there is no heat exchange, or heat exchange from one to the second is same as that coming from second to the first. So when they're in thermal equilibrium, that means they have the same temperature. Okay, so that is another way to define what is temperature. Then you can define temperature through ideal Carnot cycle. So typically this is a Carnot cycle. You have a high temperature source and you have a low temperature sink, and heat is coming from the high temperature source to the engine, QH, and the engine does some work, W, and it actually gives away heat of QC to the sink, which is at lower temperature. So typically, you write that the work done by the Carnot engine as the high temperature TH minus the sink temperature TC into the change in entropy of across the system. So you can say that temperature is a quantity whose difference is proportional to the work obtained from a Carnot engine operating between a source and sink. So this is another way you can define temperature. Right. So what is the importance of temperature measurement? As you know, temperature affects our life in a very significant way. In day-to-day life, we talk about what is the ambient temperature, what is the body temperature, what is the oven temperature, and so on. And it also has very important industrial and technical applications. For example, you are concerned about temperature of an engine, temperature of a product when it is getting manufactured. And when you talk about temperature, both steady as well as transient temperature are important. Right? So how do we measure temperature? We can measure temperature either using contact method or non-contact method. Contact method is something where the actual probe is in physical contact with the source or the surface whose temperature we want to measure. Okay, like you use a thermocouple to measure the temperature of a hot surface. So here there is physical contact between the thermocouple and the surface. And the principle, as you will see subsequently, is based on the thermal equilibrium between the surface and the thermocouple tip. In non-contact method, you are basically not physically, contacting the probe and the source, which temperature to measure. Instead, there is it happens through maybe an optical electromagnetic radiation. So, for example, in infrared radiation and optical radiation, as you would see towards the end of this chapter, there is only electromagnetic radiation exchange that happens between the probe and the surface, and through which we are able to measure the temperature. There is no physical contact. The other thing to note about temperature is that temperature is an abstract quantity. You can't really, see temperature, unlike length or mass. We can only feel it, right? And the temperature can be measured by measuring the change in various dependent properties. For example, we can look at change in the physical property, like change in the length of a rod, for example, and we can predict what is the temperature. We can look at change in the thermophysical properties, for example, the volume expansion of mercury in a thermometer. That's an example where the thermophysical property measurement is exploited to actually measure temperature. And the third is one can look at pressure measurement, volume measurement, resistance measurement, and then indirectly predict what is the temperature. So let us look at temperature scales. So typically temperature is measured in various units. The first one is Celsius or centigrade. And the second one is Fahrenheit. The third one is Kelvin. And the fourth one is Rankine. Okay, so these are typically four important temperature scales that are used. And you can actually relate each of them with the other temperature scales. Two of the most commonly used are centigrade and Fahrenheit. For example, if you go to America, most of them talk in terms of Fahrenheit. In fact, we talk about temperature, weather temperature, they don't talk about centigrade, they talk about Fahrenheit, right? And Europe and probably the rest of the world, they talk about in terms of centigrade. So this Fahrenheit and centigrade can be, related. So typically, degree Fahrenheit is 9/5 into degree centigrade plus 32. Similarly, Kelvin and degree centigrade are related. So Kelvin is basically degree centigrade plus 273.15. Okay. So you talk about absolute zero temperature. Absolute zero temperature here is the temperature at which this temperature will be 0 degree Kelvin. That means in terms of centigrade, it will be minus 273.15 degrees centigrade. Then you have Rankine scale, which is degree Fahrenheit plus 459.69. So if you talk about the Fahrenheit and centigrade, these scales are actually based on the number of increments between freezing point and boiling point of water. Okay. So you know that the freezing point of water is 0 degrees centigrade, the boiling point is 100 degrees centigrade. So you can talk about any kind of division between 0 degrees centigrade and 100 degrees centigrade, and that is how you can have these two scales. So Celsius has basically 100 units, 0 to 100, but Fahrenheit will have 180 units between these freezing point and the boiling point of water. Okay. And as he said, absolute centigrade scale is known as Kelvin scale, and absolute Fahrenheit scale is known as Rankine scale. So this table basically summarizes how the different temperatures are related. You can see that the freezing point of water is 0 degrees centigrade, which is 32 degree Fahrenheit. And now the boiling point of water is 100. So you can see that you can have 100 divisions here. 0 degree, 1 degree, up to 100 degree. But if you talk about Fahrenheit, it starts from 32 and goes to 212. So the division is basically 212 minus 32, that is basically 180. So when we said 180 units, that is what we mean, 212 minus 32. So these Celsius and Fahrenheit scales can also cross over, meaning there is a temperature which is the same in Celsius scale as well as the Fahrenheit scale. Okay, so this you can find just by saying that, okay, if my degree Fahrenheit is equal to degree centigrade, so you can write degree centigrade equal to 9 by 5 into degree centigrade plus 32. So you can find the degree centigrade will be minus 40 degrees centigrade. Or you can say that degree Fahrenheit is 9 by 5 into degree Fahrenheit plus 32. So in that case also, you will find degree Fahrenheit is minus 40. So it is minus 40 degree Celsius, which is same as minus 40 degree Fahrenheit. And if you go absolute zero temperature, which is at minus 273, then you actually reach the absolute zero temperature. And similarly, in Fahrenheit, your absolute scale will be minus 460, because that is where if degree Fahrenheit is 0, your Rankine is going to be 460 degrees. And so Kelvin is basically 0 degrees centigrade is 273 Kelvin, 100 will be 373, minus 40 will be 233. And minus 273 is 0 degree Kelvin. And Rankine is basically 32 degree here. Your Rankine will be 492, and your 212 will be 672, minus 40 will 420, and minus 460 will be 0 degree Kelvin. So you can see that the 0 points on Kelvin and Rankine scales are the same physical state. So here, 0 degree Kelvin and 0 degree Rankine correspond to absolute zero temperature. That means you can actually write that since the 0 degree scales coincide, you can actually write the T2, any temperature T2, over any other temperature T1 in a Rankine cycle will be same as basically T2 minus T1 in a Kelvin cycle, because you can see that, for example, here 373 minus 0 divided by 233 minus 0 will be equal to 672 minus 0 divided by 420 minus 0. So right from there you can find T2 over T1 again is T2 over T1 Kelvin. So
Sir,
this
when we
only-
say absolute,
yeah,
sir, when we say absolute zero, that means there is no kinetic energy in the system, right, sir?
yeah,
that right?
absolute zero, where all the molecules cease to move, and basically there is no kinetic energy in the system.
Thank you, sir.
Okay, so we now talk about the different temperature measurement methods. So we have basically three different types of methods that we'll discuss in this chapter. First is the mechanical method. Second one is electrical method. Third one is radiation methods. In mechanical methods, we have because we can just measure the change in the physical properties, so mechanical properties. So we can talk about expansion of solids, where we talk about solid rod thermometer and bimetallic thermometer. Okay. And both these are based on the principle that most solids will expand when they are at a higher temperature. Then you have expansion of liquids, because liquids should also expand when there is an increase in temperature. So based on which you have the liquid in glass thermometer. And then you have the temperature measurement based on expansion of gases. So you talk about gas thermometer. Okay. Then we have electrical methods. In electrical methods, we talk about electrical resistance thermometers, that is RTDs. The full form of RTD is resistance temperature detector. So here, based on the temperature, the electrical resistance of the material is going to vary. Okay. Typically, the resistance is going to increase with increase in temperature. So by looking at the resistance of a material at a higher temperature, you should be able to predict what the temperature is. Then you will have thermistors. Thermistors are made up of typically semiconducting materials like alloys of nickel, cobalt, and so on. And typically, the RTDs, the temperature would increase in temperature, would increase the resistance. Whereas in case of thermistors, the increase in temperature will reduce the resistance. Okay. And this we'll study in detail, maybe in next class. Then we have thermoelectric effects. So thermoelectric effects basically are the principle behind which the thermocouples work. Right? So typically you have two dissimilar metals which are joined at the ends, and if you subject these two ends to two different temperatures, then there will be an EMF induced between these two ends, and which you read, and the EMF is basically proportional to the temperature difference. So you have higher and higher temperature difference between the ends, you have higher and higher EMF, and if you can have a calibration curve between the temperature difference and the output voltage, because if there is an EMF, you can use an EMF measuring device to actually record the output. And as the temperature, for a given scenario, if you know the EMF, you can predict the temperature from the correlation that is available. Then you have radiation methods. In radiation methods, as I said, it is a non-contact technique. Okay, so you don't really probe in unlike thermocouple or RTD, you don't physically intrude into the source, which temperature you want to measure. You just use the electromagnetic methods to predict temperature. So you will talk about total radiation pyrometer, optical parameter, and infrared IR pyrometer. So today, let us talk about the mechanical methods. Okay. So the first technique that we are going to talk about for temperature measurement is expansion of solids. So typically, if you have a solid of length L and you subject this to temperature change, typically most of the metals would actually expand upon increase in temperature. And because of that change in temperature, let's say delta L is basically the net expansion of this metal. So you can express the change in length delta L as alpha into L naught into delta T. Here L naught is the original length of the rod, and delta T is the temperature rise. Alpha is known as temperature coefficient of expansion. Okay, so this is basically a material property. This is the property of a material. Initial length is the geometrical parameter. So these two basically would decide for a given change in temperature what is the change in length. So application of this expansion of solid is realized in rod type thermostat, which we will see subsequently, and typically for operating an electrical switch. Okay. The temperature coefficient of expansion alpha that you have here is typically very small. As you can see, this table, it is tabulated. So you can see that for aluminum, it is 23, in copper, it's 17, brass, it is 19, and iron, it is 11.8. And but you have 10 to the power minus 6 per degree centigrade. Okay, for example, for aluminum, it will be 23 into 10 to the minus 6 per degree centigrade. That is the value of alpha. So it is actually a very small quantity. Since alpha is small, even if you choose, L naught to be several centimeter, but since alpha is 10 to the minus 6, and delta T can be something like, 10 degree or 100 degree, So because alpha is very small, this change in length happens to be very small. Okay, so you need to have a very sensitive method of actually measuring this delta L. And for small temperature ranges like 1 degree, 2 degree, you may not have a noticeable delta L to actually measure. And that is one of the major limitation of this method of temperature measurement that is based on expansion of solid. But we can have a calibration curve between the temperature and length, and for an unknown length, you can actually very well predict what the temperature will be. The other thing to notice about the value of alpha for various materials here is that if you look at INVAR, the value of alpha is very small. Okay. It is about just 1.2 into 10 to the minus 6 per degree centigrade. So that is why, INVAR is typically used to make precision instrument, because if you make precision instrument out of INVAR and if there is a change in temperature between, let's say, winter and summer, the precision instrument is not going to be affected much, because the coefficient of expansion is very, very small. And it is also used in making watch needles, because you have to ensure that the length of the needle remains nearly unchanged between summer and winter. So that is why invar is a material which has very specific and interesting applications. Then another method that you can choose to measure temperature is called bimetallic thermometer. It is called bimetallic because typically you have two different metals which are bonded together, something like this that you see in this picture here. So you have metal 1 having a thermal expansion coefficient of alpha 1. Then you have metal 2, which has a thermal expansion coefficient of alpha 2. And you can have different thicknesses of these metals. So H1 is the thickness of metal 1 and H2 is the thickness of metal 2. And typically in a bimetallic thermometer, these two metals are bonded together at this interface. Okay, so you bring metal 1 and metal 2, you actually bond them across this interface to form a composite laminated beam structure. And what is important here is that when this is bonded, these two laminated structures are bonded, metal 1 and metal 2, the temperature at which this bonding happens, you have to ensure that the beam is actually straight. Okay, because if the beam is initially deflecting when it is manufactured, then it will give erroneous results. So make sure that initially it is flat and straight. And when the temperature is higher than the bonding temperature, the temperature at which they were bonded, then you would see that the beam will bend in one direction. Okay, something like this, right? So this will bend something like this. So, now which side it is going to bend, whether to the metal 1 side or metal 2 side. So typically, always it will bend to the side that is having lower thermal expansion coefficient. For example, here, metal 1 is having higher expansion coefficient than metal 2. So that is why it actually bends near to metal 2. So here you see that your alpha 1 is greater than alpha 2. And what is important is this radius of curvature, that is rho. And this rho has been expressed as this. Okay, and if you look at the book Dublin, so there has been some attempt to actually derive this formula, which I am not going to talk about here in this course. But you can actually, derive an expression for the radius of curvature of this bent column. So that is expressed as 3 into 1 plus RH whole square plus 1 plus RH into RE whole into RE square minus 1 over RH RE whole into H. H is basically the total thickness H1 plus H2. Okay. And divided by 6 into alpha 1 minus alpha 2 whole into 1 plus RH square into delta T. So here H is basically the thickness ratio, that is H2 divided by H1, and R, which is basically the elastic modulus of metal 2 to elastic modulus of metal 1. Now, initially the beam is flat. Okay. That means the radius of curvature is infinite. And when there is a temperature difference, since alpha 2 is less, you actually have a bent structure of this beam. Now, this radius of curvature, it actually depends on various parameters. You can actually vary the radius of curvature by changing this RH. As you can see from this expression here, as RH increases, you can actually decrease the radius of curvature. That means you can have a very tight radius. Okay, it will bend more. And also, if you increase alpha 1 minus alpha 2, right, the thermal expansion coefficient difference, if it increases, then also the radius of curvature is going to be smaller. That means it's going to be bent more. And thirdly, of course, if the temperature is going to be higher, then the radius of curvature is going to be lower. So this is an example how the bimetallic thermometer is used in a thermostat application. So typically this is used in a colder countries where you need to heat the ambient. Okay, so this is basically the ambient where this hot gas comes in. Typically they produce hot gas by flowing the air around hot water. Okay, and so this hot gas come in and goes through this valve, and this is basically your process space, maybe your room, for example, that you want to heat. So this gas goes through this valve. Now, when the temperature is, let's say you just switched on the thermostat and now the hot gas is coming in, and you have set the temperature, let's say, to 20 degrees. Initially, the room temperature was, let's say, 10 degrees. Over time, the temperature increases. So when the temperature increases, as you can see that this inward rod is there. Inward rod is part of the valve. Okay. Why inward? Because it will not change its dimension for a change in temperature. But it is encapsulated inside this casing, which is made out of brass. And you can see that brass has a very high expansion coefficient of 19 into 10⁻⁶. So basically, when the temperature the room has now heated up, then this brass is going to expand faster, much faster compared to the inward. When this brass tube actually expands, it is going to pull the inward rod with it. That means the valve is going to close. Okay. Now, if the ambient cools down, okay, so the valve gets closed because set temperature 20 degrees has reached, the valve goes down. But this ambient, which is basically the room, also has heat exchange with the surrounding. That means outside your house, for example, outside your room, temperature is much cooler. So essentially, this process space temperature will go down. When the temperature goes down, this brass rod will now shrink. And when the brass rod shrinks, the valve again opens up. Okay, so when the valve opens up, again the hot gas can come into your room. So that is the principle behind thermostat, how thermostat works. And the sensitivity of this thermostat can be increased in various ways. And one way to increase sensitivity is that instead of using a straight tube, you actually use a helical tube. So one advantage of helical tube is that with very small change in temperature, each segment of this length of this rod is going to expand. So because a long rod can be effectively squeezed over a shorter length by using this helical structure. So the overall length is higher, and as you know, the delta L is proportional to the initial length. So in the helical arrangements, in the initial length is very high, you see that the change in length is going to be amplified as compared to, let's say, just a straight rod. So this kind of approaches you can use to actually enhance your response to change in the temperature. So now we talk about ideal gas thermometer. And these ideal gas thermometers have typically a tank, a small tank, which is filled with helium, let's say. And this tank is connected to a pressure indicator. Okay. So that means you are able to continuously monitor, accurately monitor the pressure inside this tank. And this tank is basically exposed to the source temperature. That means the process space temperature. And typically this ideal gas thermometer obey ideal gas equation, which is basically P into V equal to mRT. And in this case, the volume is fixed because this is a rigid container. So V is constant. Okay. So you can write T equal to P into V divided by mR, and V is constant. So you can write that T by P is equal to constant because V is constant, and for a constant mass of gas and gas constant, the whole thing is constant here. So you can write that T by P is constant, right? So in other words, you can write that temperature over some reference temperature will be equal to pressure divided by some reference pressure. Okay. And this reference temperature can be any reference point. For example, triple point of water, which is 0.01 degrees centigrade. So if you expose this container or the tank to 0.01 degrees centigrade, known temperature, the reference temperature, the corresponding pressure indicated by this dial is going to be the reference pressure. So you know the temperature, reference temperature and the corresponding reference pressure. Now you want to measure certain temperature of some ambient. So you expose this tank to that ambient. When you expose this tank, what do you expect to happen? It is going to, let's say you are going to increase the temperature of the process space. So when this temperature is higher than the reference temperature, the gas inside this tank is going to expand. So your pressure is going to increase, right? So basically you write that T equal to Tref into P by Pref. Now these are reference conditions, and for an increased pressure because of the exposure of this tank to a higher temperature, you can predict what the temperature is. Okay. So typically the relationship is expressed here. This is temperature axis in Celsius. This is pressure axis. And you can see that here your temperature and pressure are linear to each other. So you can see that this is the typical characteristic. And these three different cases are actually for different kind of gas, for example. So for different gases, the slope of this is going to be different because the gas constant R is, which is universal gas constant by molecular weight. For different gases, since M is going to be different, your R is going to be different. So even for a same mass, since R is specific to the specific gas constant, you will see that depending on the gas, they will have different characteristic curves here. Okay. So basically, if you see where they intersect the T equal to 0 line, this is T equal to 0 line. So they that means even if the temperature is 0 degrees centigrade, still they have some finite pressure, right? Because the molecules do not stop at 0 degrees centigrade. So there has to be some finite pressure. And when you extend these lines, all of these have to converge at minus 273.15, because this is the absolute zero temperature where your pressure goes to zero. Okay, so pressure is zero only when your temperature is minus 273.15 degrees C. Right, so you see. Then we have liquid in glass thermometer. Typically, this is how a thermometer looks like. You have a bulb at the bottom end of the thermometer. Then you have a stem, and at the other end you have a safety bulb. Safety bulb is for safety, because if you, let's say, accidentally expose it to very high temperature, this mercury should expand and then should have some buffer space to, get stored here in case of sudden change in temperature. Because if this is not there, then if the pressure suddenly increases, this capillary can break, and in that case, mercury will just splash out, and mercury is very dangerous. So that is why you have this safety bulb at the other end, and you have the capillary tube, and there are, and this portion is called the stem. And there are these scales which are all over this, all along the length of the capillary. Okay. So this is typically the construction of a thermometer. The principle of thermometer is the differential expansion of the liquid. Okay. That means the liquid that is inside this thermometer, which is mercury, expands much faster than the glass material itself. Because if the mercury and glass material both expand the same way at the same rate with temperature, then you won't basically see the mercury rising. The mercury rises because the mercury expands much faster compared to the expansion of glass as a material with increasing temperature. So typically, you use mercury, which has a thermal expansion coefficient of 0.1819 into 10 to the power minus 3 at 20 degrees centigrade. And this is, you should notice that this is about 1,000 times or 100 times to 1,000 times higher compared to the values that you see for solids, because this is about a minus 6. And here you see that it is about minus 3. Now, if you talk about ethyl alcohol, that has a thermal expansion coefficient which is 10 times higher than mercury. Okay, but yet we do not use ethyl alcohol in the capillary, and that is because alcohol is very volatile. So that means if there is a very, very minor gap, or while filling it, you have the challenge of, losing the alcohol that you want to fill in. Second is that alcohol wets glass. So when temperature drops, still some liquid stays over glass. So what it's saying is that, if you fill this kind of capillary with alcohol, let's say it has reached some very high temperature. Now, if you reduce the temperature of the ambient here, this would not really come down easily because of the wetting problem. Okay. And the last reason is that mercury is very stable over a wide range of temperature. That is why we can use typically mercury, not alcohol. The ability of a thermometer to actually respond to the temperature change is given by what is called response time. And the response time depends on the time constant. So in fact, for a thermometer, we can estimate the response time from Newton's law of cooling. So let's say this is the thermocouple bulb, and which is at some initial temperature T0. Let's say it is exposed to an ambient which is at a higher temperature than the initial temperature T0. So thereby there is going to be heat that is flowing in to this system, and the temperature is a function of time, which is given here. T is a function of time. Now you can write down this energy balance, which is the heat transfer coefficient into the surface area of this object times the change in the temperature, the ambient temperature minus time T as a function of time at a particular time, is going to be the rate of change of the energy inside the system. The mass of the system into the specific heat into change in temperature. So you can define, so here you can see H is basically heat transfer coefficient, S is the surface area of the bulb, and M is the mass of the bulb, and C the specific heat. So one can define the time constant tau as the ratio of the product of mass times specific heat divided by the heat transfer coefficient times area. And once we say that this is the time constant, this actually is a measure of the response of a system. How? One can write down again this TA minus T into dt. This dt comes here, so TA minus T into dt. The right hand side will have MVC divided by HAS, so which is basically tau into dt. So from here, your dt by dt, the rate of the temperature with time is TA minus T over tau. And if you integrate this equation with the fact that temperature at T equal to 0 is T0, then you get this equation. So this is how the temperature of the system is going to change with increase in time. So you can define this time constant, as we said, is M into C over HAS. So this time constant is basically, when we studied the electrical circuit, it is basically resistance time capacitance. So the 1 over HAS, the 1 divided by the heat transfer coefficient into the surface area is known as thermal resistance. And the numerator, mass into specific heat, is known as thermal capacitance. So the product of thermal capacitance into thermal resistance gives you the time constant. So for a typical thermometer, the bulb will have a diameter of about 3 millimeter, let's say 3 millimeter. Length will be about a centimeter, let's say 12 millimeter. And density of mercury is 1.355 in the 4 kg per meter cube. So you can find the mass of the bulb, that is, you know the diameter and you know the length. So you can say that this is about pi d square by 4 into L, that gives you the volume, and into the density of glass will give you the mass, which is 1.15 minus 3 kg. And the surface area of a typical thermometer is about 1.27 minus 4 meters square. So you have the volume, you have the mass, you have the surface area, and then the specific heat is about 139.4 joule per kg Kelvin. So if you plug in all these here, you see that you know the for water as the fluid, and you can, for water, the H is about 750 watt per meter square Kelvin. So for this, the time constant will be only 1.7 seconds. It says that if you have some kind of thermometer, and then you are basically dipping it into initially it is at 25 degrees in air, and you are dipping it in a water bath which is at 50 degrees centigrade, then it will take about 5 times this time constant. That is about so this is approximately equal to 2 seconds. So it will take about 10 seconds to reach the 50 degrees centigrade temperature. Whereas if you now initially the let's say the thermocouple is dipped inside water, this is the second case, and you take it out to about 25 degrees centigrade in ambient, there it will take a much longer time to cool down. So it takes about 600 seconds. Okay. Now, why this is different? When it is heating, it is actually taking about 10 seconds. And when it is cooling, it is taking about 100 seconds. That is because of the ambient heat transfer coefficient. Typically, when you bring the thermometer, which is initially in air, into water, so water has a heat transfer coefficient is about 750 watt per meter square Kelvin. But in the second case, when you bring from hot water to still air, the heat transfer coefficient is only 10 watt per meter square Kelvin. So that is why you take, your temperature equilibrates for the thermometer very quickly, about 10 seconds in water, but it takes about 600 seconds to cool down in air. So let us stop here in interest of time. And if you have any question, we can discuss, take a couple of questions.
So, sir, one small request.
Yeah.
One small request. Actually, our end sem falls on the Saturday and Sunday.
Okay.
So we request, can you prepone 1 week before, sir? 1 week before prepone your exam.
1 week before or after?
Recording stopped.
Can you say that again?
Sir, our end sem, sir, our end sem,
Sixth,
final exam.
Final exam. Okay.
Final exam.
Okay.
So
Okay.
yours exam is on 30th and 31st of 30th of November, I think. And Manivan sir exam is on 31st.
Okay.
So back to back exam.
Mine is scheduled on 30th of November.
Yeah, I think so. Yes, correct, sir.
Okay.
Correct,
So
sir.
you want it to be preponed by 1 week.
Yes, sir. Yes, sir.
Okay, let's see. 13th of November is basically Saturday.
Yes, sir.
So you want it to have it on 23rd of November, right?
Yes, sir.
Yes, sir.
Exactly.
So
23rd or 24th? 24th, sir. 24th.
Okay, so I mean, whatever date you want to pick, can you intimate that to the code office?
Yes, sir. Yes, sir.
And if code
Sure, sir.
office agreeing to that, it is absolutely fine with me. You can tell them that you have spoken to me and I am okay with that. And
Okay.
once they approve, then we can do it. It's not an issue.
Thank you, sir. Thank you very much. Thank you, sir.
Okay. Yeah. Okay. Thank you all. If there is no question,
Thank you,
then
sir.
we'll meet again tomorrow.
Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, sir.